Okay, so the work I'm going to talk about today is joint with Peter van der Ven, whose postdoc at Southampton was supported by EPSRC, so thank you to them. I'm going to start by talking about the type of experiment that I'm thinking about and give you an example, and then I'll look at some different modelling strategies for dealing with a correlated response, and in particular I'll focus on marginal modelling. We'll look at the design criterion and some methods of finding designs, and all these designs will depend on the model parameters, rather like we heard in the last talk, and so we'll talk about some ways of trying to overcome this. Okay, so our example comes from the aeronautics industry, and it's a study to investigate the factors that affect the cracking of a coating on an engine bearing in an airplane engine. So the schematic shows us the experimental setup. We've got a pair of bearings here which are connected to a motor which spins them round, and then the spray gun sprays the coating onto the bearings. There are three different factors that the engineers wanted to investigate: the distance the spray gun is from the bearings, the angle that it sweeps between, and the speed at which it sweeps between that angle. And for each bearing, our outcome is that it either passes or fails some visual inspection. So we've got a 0-1 response. So our experimental unit here that we can apply our treatments to is a pair of bearings, and the response we're going to observe will be the number of bearings which pass, which will either be 0, 1 or 2. So we can think of this as a binomial with two trials. The engineers could do 16 runs, but these couldn't all be done on one day or in one session. They had to be split up into 4 different sessions for mornings and afternoons, and in between each session they would reset the equipment. So we can think about these as blocks, having 4 blocks of 4 runs. The engineers weren't really interested in trying to understand the variability between these blocks because they didn't have any meaning. They were just arbitrary afternoons and mornings. So the assumptions we're going to make about this experiment are that our sessions, our mornings and afternoons, are a random sample from the population of all possible sessions. Observations within blocks or sessions may be more similar than observations from different blocks, and the way we're going to incorporate this is through assuming perhaps that pairs of observations within a block can be correlated, whereas pairs of observations from different blocks are independent. So if we just take a step back, if we didn't have that correlation structure, we didn't have our blocks, then we could use a GLM to try and analyse our experiment. So basically a GLM has 3 components. Y follows a distribution from the exponential family. We have a linear predictor and a link function which relate our explanatory variables through to the mean of this exponential family distribution. So an example that might be appropriate for this kind of bearing experiment might be probit regression, where there could be some thresholding process that's deciding whether or not these bearings crack. So here Y would be a binomial. We'd have some number of trials, here it's 2, and some success probability P, and we'd relate the success probability back to our explanatory variables through a link function here, which is the inverse of the standard normal CDF. Now, there's been quite a lot of interest in designs for GLMs, originally focusing on just 1 or 2 variables, but more recently there's been quite a lot of work on designs for experiments with more variables, either looking at kind of a weighted average of criteria, clustering the design points of designs that are optimal for particular parameter values, or doing some kind of sequential design. So if we didn't have this correlation structure, we could use the GLM models, and we can use some of these ideas for designing the experiment. If we had continuous data that followed normal distribution, then we could use some of the results on block designs for random block effects to design our experiment. So this is the other side of the coin. Here we're assuming, okay, we have the correlated data, but it follows a normal distribution. The kind of methods we might look at would be the approach that Cheng suggested, where we restricted the number of distinct treatments to the number of parameters in the model. The kind of algorithmic search ideas that Huss and Vanderbroek worked on and Steve talked about earlier, and also Trinker and Gilmore's paper, for instance, on allocating a factorial are designed for the factorial treatments to blocks optimally. Okay, but we're not in either of those situations, unfortunately, because we've got non-normal data and it's correlated. So we have to do something else. So if you look in the literature, there are pretty much two basic modeling strategies for non-normal correlated data. You either use a conditional model where you introduce some random effects into your linear predictor, and this Z matrix is kind of zeros and ones allocating treatments to blocks. And here you might be using a generalized linear mixed model, and there's been a little bit of work on design for those by Owens and co-authors, or you might use an HGLM. We're going to look at marginal models, which don't actually assume a distribution for the effects of the blocks. Instead, they just assume a marginal model for each individual observation. They're usually fitted using generalized estimating equations, which are particularly well known in the social sciences, but they've also been applied to industrial examples as well. So that paper's in JQT, for instance. Okay, so GEs consist of then a marginal mean and variance relationship for each observation, which is generally taken from the appropriate GLM, and what's called a working correlation matrix R, and this is what tells us how observations within a block are correlated. Okay, this is going to be block diagonal because we're going to keep this assumption that observations in different blocks are uncorrelated. What they don't have is a joint PDF for all the observations. Okay, so we don't make any assumptions about their joint distribution, and so that means we don't have a likelihood function, and we can't use MLE to maximum likelihood estimation to get our parameters. So the kind of experiments and situations where GEs might be appropriate are when our blocks are an unknown a random sample of blocks for some larger population. The actual effects of the blocks themselves aren't of interest because we're not going to explicitly model those, and so the aim of our experiment needs to be to estimate the marginal effects of the variables. So that's the effect of the variables averaged across the population of blocks. So here's the estimating equations for beta, our fixed effects in our model. And you can see they are just a generalization of the score equations for a GLM. The generalization being we've got our working correlation matrix sat in the matrix W. We also have estimating equations for our correlation parameters. So for instance, if we assumed an exchangeable correlation structure where all observations in a block have the same pairwise correlation, then we just estimate that pairwise correlation by pooling the sample correlation of the residuals across all the blocks. And asymptotically, our parameter estimators are going to be asymptotically unbiased, and they're going to follow a multivariate normal distribution where the variance-covariance matrix is the inverse of this matrix here. So this is going to be a lot like the information matrix that was talked about in the last presentation. So let's try and relate this back to our bearing example. So here our marginal model might be a probit model again with 16 runs, each of which has 2 binomial trials. So we can model our mean and our variance. Those marginal relationships are going to come from that probit model. Let's stick with an exchangeable correlation structure. So our within block correlation matrix is going to have this form, and we're going to have this block diagonal correlation matrix for all the observations. Now when we think about alpha, it's a lot tougher, well, I think it's a lot tougher, to think about pairwise correlations for non-normal data, for data that is not continuous particularly, because the correlation depends upon for instance, in a 0-1 case, the correlation is going to depend upon the marginal probabilities of success for the individual observations. So Chakotay and Joe actually suggest not thinking of alpha as the actual pairwise correlation, rather as some kind of overall measure of the relationship between two observations. And in fact, they actually suggest in the estimation procedure you might want to fix alpha at some value you think is sensible rather than estimating it from the data. Right, so that's basically the model we're going to try and use. Now, when we look at analysing small experiments with this kind of model, we do come across a problem, and it's a problem that's quite well known for uncorrelated data. Basically, with binary or binomial data, you have quite a high chance with a small experiment of getting a line or a hyperplane in your design space that completely separates your points into those that give you a 0 response and a 1 response. And if you do that, you're going to get infinite parameter estimators and infinite standard errors for those estimators. So for uncorrelated data, like I say, people know about this, and there's quite an effective solution via adding a penalty to the likelihood and then doing maximum penalized likelihood instead. For the correlated data and the GEEs, we actually suggest that we could extend the method of Clogg et al. And Clogg and his co-authors. That was for GLMs. Basically what we do is add some pseudo data or a prior. They called it flattening constant. So we basically, to each of our treatments, we add a bit more data where we say there's a particular number of 0s and 1s. And then with this adjusted data, we can use the standard algorithms to fit our model, and we guarantee to get estimates existing. And if you want to, you can think about this as coming by adding a penalty or a conjugate prior onto the quasi-likelihood that's implied by our estimating equations. So these are the adjusted estimating equations we would then work with. Here are the original ones, and here are the estimating equations from our pseudo data or our prior. And because we know we're not separated here, we can't be separated when we add more observations in with our original data. So this gets around the problem for us. Does it work? Any sensible measure in terms of the estimates you still get? Well, we've investigated this through simulation studies. So here's an example where we did 10,000 simulations from a probit regression again. So we've got 3 variables included in our model, and we've also got the interactions between them, and these are the values for those variables. And we generated data with pairwise correlation 0.12. And our design, and I'll talk more about how we find these designs in a moment, that has 16 binomial runs split into 4 equal blocks, and we found our design assuming our working correlation would be 0.2. So the plot gives the results from the simulation. The blue triangles are the true values of the parameters, and the black dots are the average estimates from the 10,000 runs. Looks like a bit of a cheat because they lie what's exactly on top of each other, but this was come by using basically an automatic choice of adjusted data by adding in as much data, extra data, as we had parameters in our model. And so we're getting pretty good average estimates from our simulation. The bars are asymptotic confidence intervals, and certainly for the 4 larger effects in the model, they don't contain 0, so we aren't making any type 2 errors about those. And the numbers next to the bars just tell you the actual coverage we got for those intervals. So they're pretty close to the 95%. So it looks like this method can do a pretty good job for overcoming this separation problem for small experiments. Okay, so that's how we're going to analyze our experiment. How we're going to design it? Well, we'll think about using d-optimality. So we're going to maximize the determinant of this information matrix that we looked at before. Now obviously this depends on our model parameters and our working correlation, and so our designs are going to be locally optimal. And we can define the efficiency of any design in terms of a locally optimal design through this ratio, just a ratio of the objective functions. So for block designs, there are basically 2 strategies we can take for our design. We can find an exact design, so that's going to give us the endpoints we should actually run in and put them into B blocks for us, or we can find a continuous design which will give us an optimal set of blocks and the weights that we should use with each of those, which tells us the proportion of experimental effort we should apply. If you use continuous designs, then you can establish a general equivalence theorem, which you can, in theory, then use to check the optimality of designs. But what I'm going to concentrate on is exact designs that we could actually use in this bearing example. And I'm going to look at 3 different ways of finding these designs. And these are basically analogous to the methods I discussed earlier for when our response follows a normal distribution. So the first is to restrict to k treatments, where k is the number of parameters in our model. And if we do that, the d-optimal design problem decomposes into selecting a treatment design and a block design separately. We can just do an algorithmic search of the design space using some sort of computer optimization to find the best exact design, or we can take the optimal design for a GLM and then allocate it to blocks to get the most efficient design possible. So we'll look at these three methods, we'll compare them on this example again, which is the same probit model as we used for the simulation. And again, we'll look for runs for 16 designs in 4 blocks of 4. And we'll find designs for alpha is 0.2, but then we'll look at the robustness of the designs to alpha as well. Right, so we think about the minimally supported designs to start with, where we restrict to having the same number of treatments as observations. If you do that, you can show that the determinant decomposes into these two parts. The determinant, this is essentially the determinant of the information matrix for a GLM, and this is the determinant for the information matrix when we have, we're trying to estimate K treatments in B blocks. And so we can then solve these two problems independently. We can find an optimal GLM design using the kind of results I talked about earlier, and we can find an optimal block, the optimal arrangement of that designed blocks. For example, using a balanced incomplete block design, if one exists, that would be D-optimal. Or we can find the design from an interchange algorithm. So this is the design we get out for our example using this method. So here are our 4 blocks. The 2 axes are obviously the values of x1 and x2, and the third variable changes with the color. So there's only 2 different values of x3 in this design. In fact, there's only, that's not true, x1 has a few different values, but x3 only has 2 values. And all the design points are on the boundary of the design region. We can also just do an algorithmic search. We use simulated annealing. So we fix a number and sizes of blocks, and then for each particular point in our design, we just do a little random perturbation, and we accept that adjustment to that point if it improves the design, and we still accept it even if it doesn't improve the design with some probability inversely proportional to the decrease in the design performance. And that probability and the size of the perturbation decreases as we go through our search. So we end up with a greedy algorithm homing in on a good solution. And we obviously would want to run this more than once to try and make sure we avoid local optima. So here's the design we get using an algorithmic search. So one of the big differences between this design and the previous design is we aren't restricting the number of treatments we can have on the number of support points. And the design does look a bit different. In particular, it's got 3 different values now for x3, not just 2 different values, and we've got a point here in the interior of the design region, which we didn't have for our minimally supported design. So our final method is just to find our optimal design for our corresponding GLM, and then allocate that to blocks using an interchange algorithm to try and get the maximum D efficiency. And the design we get out of this looks a lot like the design we got through doing an unrestricted algorithmic search. Again, 3 values of x3 and at a point in the interior of the design region. So certainly the algorithmic search design and the optimal allocation of an unblocked design, they look quite similar. How do they perform? Well, we can see that if we look at alpha as 0.2, they're all obviously highly efficient. The algorithmic design is the best one we were able to find, and the other 2 perform very well compared to it. It's interesting to see what happens when we change alpha. So what we're going to do is we're going to adjust the value of alpha, which remember is our working correlation parameter, between 0 and 0.8, and we're going to not find different designs. We're going to keep the same design we found for alpha is 0.2, but evaluate it under these different values of alpha. And if we do that, we can see that the algorithmic design and the allocation of the optimal unblocked design, these perform very well for the whole range of alpha. The minimally supported design also performs pretty well, but it is slightly less robust to alpha than the other 2, just a little bit. Okay, so the designs perform very well for a range of alpha, so you might well then ask the question, did you need to worry about those blocks when you designed your experiment? Could you have just taken your GLM design and treated it as a completely randomized design? Well, what I've done here is take a sample of 10,000 different allocations of the optimal unblock design to 16 blocks, sorry, 4 blocks of 4 runs each. And I've just picked them at random, okay? So there were about, somewhere between 2 and 3 million combinations in total. I've looked at 10,000 of them here. And so what you can see, if you just then block your design at random, okay, you're not necessarily going to go too badly when the working correlation is low, but as your working correlation gets bigger, you've got quite a tail on these distributions. So potentially, if you ignored the blocks, you could end up with a very inefficient allocation of units to blocks if you then were worried about them in the analysis. So it is worth thinking about the blocks when you design these experiments. Okay, so if I run late, then of course I'm setting a bad example for everyone else. So I hope I can finish in 5 minutes. So all the designs we've looked at so far have been de-optimal, but they've been dependent on the value of the model parameters. Okay, they've been locally optimal. So one way we can look at overcoming this dependency is to use this kind of pseudo-Bayesian criterion where we average our local objective function across some prior on the parameter space. And we're going to look at 2 different ways of finding designs under this kind of criterion. The first is to optimize this criterion for our GE model with blocks included, and we'll do it for a given alpha. And our second way is to optimize this just for the GLM model, the corresponding GLM, and then allocate that design to blocks for a particular alpha and beta this time. And the beta we'll choose will be the centroid of our parameter space. Right, so we've got 2 lots of designs to look at. Again, we've got our 4 blocks. So this is the design which comes from just doing an algorithmic search to optimize that particular objective function, pseudo-Bayesian objective function. So you can see we've got more distinct points now occurring in our design. We've got 4 different values of x3, for instance, and we've got extra points in the interior of our design region. So it seems that trying to average across a set of models is giving us more distinct treatments. And here is the allocation of the optimal unblocked design. So this is taking the optimal pseudo-Bayesian design for the GLM, allocating it to blocks optimally. And it's pretty similar to the other one. Again, it has extra internal points and it has more distinct points, but it is slightly different, particularly, oops, go back. Oops. I always sit in the audience and go, they're inept, they can't use the pointer. It's happening to me. Okay, so if we look at these 2 designs, this is back to our algorithmically found design. Particularly these 2 blocks vary between our 2 designs. So there are some differences between finding an unrestricted search across our design region, including blocks, or allocating our optimal design to blocks. So the way we calculated that objective function was just by doing numerical integration using a 21-point Latin hypercube sample. There are different ways you could do it, and Brad has a very nice paper that says an alternative way of doing it. And the prior distribution we assumed for beta was just made up of independent uniform distributions with these ranges. So all these ranges have the same width. We've just shifted them along the real line. Now I'm going to assess the designs in exactly the way Steve says we shouldn't assess designs, but I'm going to do them by simulating from this prior. In my defense, I would say that my evaluation is completely separate from my design search. I've used a separate set of models for the design search that I had for the evaluation. And the simulation is going to be done using 10,000 models from this design space. So it should be hopefully quite accurate. So what we can look at then is we've done this for alpha is our working correlation of 0.2, 4, 6, and 8. And here we've got bar charts now. Bar charts? Yeah. Showing us, not bar charts, box and whisker charts, thank you. Showing us our efficiencies across these 10,000 vectors. So I've generated 10,000 vectors, found the locally optimal design for each one, and worked out the efficiency of my 2 robust designs. Basically, there's very little difference for alpha is 0.2, 0.4, and 0.6. It's only when our working correlation is quite high that there seems to be an advantage to actually including our blocks in our design search rather than just allocating the optimal on-block design to blocks. Okay, so in summary then, GEEs can be appropriate for analysing some experiments like the kind of industrial example I showed you, and I think I've demonstrated it's quite important to take account of blocks when designing the experiment, although it doesn't matter so much what value of the working correlation you assume. The performance of designs are quite robust to that. These methods, we've also applied these methods to other correlation structures like the autoregressive and nearest neighbour, and we get quite similar results in terms of the robustness to alpha, and the designs are also quite robust between forms of the correlation structure as well. Okay, and there's some references. Thank you.
There is time for questions.
Certainly in industry, it is often you do find that there is some binary response, and generally that probably stop you doing the DOE. So I think it's a very useful method you show. I just wondered in this example whether there was a way of constructing the experiment in a more classical way. So rather than a binary response, if the bearing failure mode was wear out, you could weigh the bearing before and after, and then fit some model to a continuous bearing.
So that is something which the company tried initially. Before they talked to us, they've done various experiments where they tried to look for a response, a continuous response, which could help them understand the cracking of these bearings, and they couldn't find one. I mean, often you will be able to find something.
Cracking is more difficult. You'd have to X-ray them and do something.
That's right.
Yeah.
I mean, the natural area to do this is sort of hardcore reliability theory, where they have frailty models and all that, all that stuff. I mean, in a way, you're setting the scene for a wider application to those sort of models. So my question is, do you have plans to do more in the reliability area?
It is something I've thought about, and there is actually a group at Queensland University who's done a little bit of work on it as well. And I actually had a chat with a astro engineer who was looking at sending up circuit boards into space and worrying about how long they would survive. So yeah, it is an interesting area.
Is David Cox still here? This is a comment based on a paper of his, so if he is, I perhaps shouldn't make it. I might have misunderstood the paper. If you're doing designs for generalized linear models, the designs, of course, depend upon the weights that come from them.
Mm-hmm.
And if the response doesn't change hugely from one end to the other, then the weights are roughly constant, so you could use classical experimental design. So it doesn't matter if they're binary responses or continuous.
Correct.
Responses.
But that does, sorry, carry on.
Sorry, yes. Perhaps I can, I'll just finish and then ask you a question. The other thing, of course, is that you might actually just be able to transform the responses to normality.
Mm-hmm.
Then, provided you're using a linear rather than a non-linear model, you would just use standard methods, whatever they are in your mind for standard methods. Like simulated annealing for de-optimality might be your idea of standard. You didn't say how much the responses, did you? Sorry, I missed your saying how much the responses changed.
In that particular
example, because you did get everything on the boundaries, and of course you don't necessarily. You have a rather peculiar behaviour with binary models with simple factors, but But if the response changes fast enough, the points do move away from that. So what kind of range of values are we looking at for probability?
Oh well, for the examples I showed, we weren't looking at terribly large betas. Let's have a look. So the model is there. So they weren't very huge, those ones. So the biggest one is 2. And in fact, what you're saying is ties in quite well, because if you think about the kind of designs we had for X3, they tended to have fewer values. And that's because it's basically got a smaller coefficient. I mean, in response to your first point about being able to use a standard factorial, if the betas are small enough. That kind of seems like you're designing for the experiment which is not going to have any effect, which seems slightly less interesting perhaps, or slightly less relevant than designing for the experiment where you think there's going to be an effect.
Yeah, okay. But it might be efficient for a larger range of parameter values, and something you really exciting you were designing for that doesn't happen. There's another article. Yeah.
To cut you off, let's thank the speaker once more.